Okay, now it's connected. There was one time I did not record any sound, and so I just want to make sure that that is not the case. All right, let's move on to the exam. Hmm? Right, right. Oh, so this person, kind of waved the cup, signaling I need to go out to get some water. Go like, well, okay, fine. And then, that should have taken, I mean, it's like just a short walk over there and then come back, that should have taken like no more than 45, 50 seconds or so. And then it took like a minute or two. I go like, that's not right. So I went outside to try to look for that person, and that person was just walking back. And then I saw the phone in the pocket. I go like, did you take your phone with you when you walked outside? And the person said, yeah, I did. I go like, that's not good. But unbeknownst to the person, I actually walked over to take a look at the exam, so I knew exactly which part was answered and which part was not answered. When that person walked out of the classroom, and then when I graded the exam, that portion was completed, but in a very strange way. Not in the way that I talk about that particular topic, but in then I typed my own question, with Google, and oh, oh, this is the answer that that person has in the test. Mm. So yeah, well, I mean, I'm trusting for the most part. Okay, so uh, but unfortunately, that person, yeah, and did not seem to realize that it was wrong. So that's the part that got me the most. Anyway, all right. So question number one is, is a test, based on simulating the circuit, with the NC and PD stuff. So we'll go ahead and take a look at the format of the question. So it is partially filled in for you already. Okay, it is partially filled in. Let me kind of magnify a little bit so you can see what it looks like. So you might want to bring a ruler with you just so they can line up the columns and the rows, a little bit more easily. But otherwise, it is already filled in. So one thing I can do is I can actually just kind of mark up um, this part here. I think I can do that. Let me do just exactly that. So I'm gonna use a different program to kind of go through this exam. There we go. The program is called, there are two. One is called Zernal, and it's a really kind of useful program. So we'll do this X2 dash 4. Yep, that's the one. Okay. All right. So I try to make the table itself, self-contained, which means, the kind of gate that you're working with, and also which pin or which port we are working with. They're all reported here. And then these numbers are node numbers. Okay. So if you have several columns of the same number, they belong to the same node. Um, so that's kind of, and then the A, B, C, D, E, F, G, H, and P, those are the names of those are the names of the ports, excuse me, not the ports, the components. Okay, so you have uh, the numbers are identifying the the node, and then this is the type of the component. This is the ID of the component, and these are the ports of the component. Okay, so those are the four things that you need to know. But for people who want to draw everything first, like, really pictorially see everything, how everything is connected, you can do so. Okay, you can do it on a piece of paper, but I'm not supplying that. Okay. Um, so we'll go ahead and take a look at this thing here. This is an NC row. Okay, so with an NC row, we're supposed to basically copy everything that is boldface, because it's a starting point. So we copy everything that is boldface to other things of the same node. So this is node 1. This is also node 1. This is also, sorry, node 0. No, those are node 1. Oh, okay. So this is a node 1. This is also a node 1. This is a node 0. This is a node 0. and so is this as a node 0. So the NC row is correct. And then on the PD row, we have to look at components where at least one of the input has changed in the previous NC row. So now we have to be a little bit more careful and make sure that we cover every single one. Um, so this NAND gate is getting one of its input pin being a 1, but we still do not know the other one. So the output is not really changed. We don't know what the output is. Um, on the other hand, with this particular, this is an AND gate, AND AND gate. So with an AND gate, if at least one input is a 0, we should know the output of the AND gate being a 0 in this case. So we're going to have to change that to a 0. And why is this tool not working? Mm, There we go. Yeah, I have to. It's not very good at aligning things, so I have to move with the same tool. Yeah, there we go. All right. So in the test from the previous semester, if a column is missing something, it is missing the entire column. So that means from here on, this is the column that I need to pay attention to. So I'm going to kind of highlight it a little bit just so that I don't forget. So we're going to highlight, this row, okay, like that. And then I'll switch back to the text tool for the next thing. Okay, there we go. All right. So we are done with the AND gate called P, and now we are moving on to the NOT gate called H. But that's already handled. So that means, if we know the input pin of a NOT gate is a 1, the output is guaranteed to be a 0. So that part is all done. So I think that accounts for every single component that I can be certain about the output. So this one I cannot be certain because only one of the pin is known and it is a 1, and the gate itself is a NAND gate. So are we doing okay so far with this? Yep. The numbers are the nodes, and then the letters are the components. So one specifies the connectivity, the other one identifies the component. So the name of the components, so these are, so from here, we know that G is a NOT gate, C is a NOT gate, H is a NOT gate, K is a NAND gate, Q is an output pin, and so on. So the letters identify the component, hmm and then the numbers, identify how the ports are connected. So the ports of the same number, they're all connected. Yeah, yeah. The assignment was color coded because it didn't have that many nodes. So with 10 nodes, or 11 actually, because I counted from 0. So with 11 nodes, color coding would not be a good idea because you would have shades of color that are difficult to differentiate. So that's why I decided not to use color coding, because color coding would also make it really hard on people who are colorblind, because people who are colorblind cannot differentiate certain shades of color. And since I'm not colorblind, I cannot evaluate whether it is a good choice of colors or not. So I just decided, let's not use color and use a number instead. Yep. Hmm? Yes. Yep. Yep. Based on the gate, right? So in this case, because it's an AND gate, if at least one input of the AND gate is a 0, the output of the AND gate is guaranteed a 0. So that's the logic behind why I put a 0 here. This one, this one is given, but it is a NOT gate. Yep, 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 exactly. But for this one, I cannot. It was unknown to begin with, but it continues to be unknown because I don't know what the other input pin is, or input port, I should say. All right, so this is PD, and then we go for NC. So transitioning from a PD to an NC means everything on node 5 should all be changed to a 0. So we look up node 5, okay, that becomes a 0. Node 5, it becomes a 0. This is the originating node 5. It was a 0 to begin with. So we are done with that propagation with the NC. This is node 6. Node 6 also needs to change to 0. So now we look at all the node 6, and this node 6 is a 0, and there are no other node 6s. Um, and we have one more. This is a node 5. Okay, we accounted for that node 5 already. This is a node 6. So we're good. Okay, everything is self-consistent. So that's the NC row. After that particular NC row, now we know yes, so we are good here. So now we know this output pin, this output port should be a 1 because we just changed both of the input ports of this NAND gate, which is called A. Like A is its ID. So because both of the input ports are zeros, so output is going to be a 1. And then we look at the NAND gate called F. The output should be a 1 2 because I didn't know whether it would be a 1 before because I only knew one of the input port is a 1. Now that we know the other input port is a 0, so one NAND 0 is a 1, so that's why we know this 1 over here. Um, for this AND gate here, we have no change because we already concluded the output would be a 0, so there's no change over here. And then for this NOT gate, we determined the output already, so there's no change over here. So that is actually concluding this particular PD row. And then we move on to the NC, which means we propagate node 7 to all the other node 7 to be a 1. And so this one is a 1. And we look for all the other node 7s, and I don't see any. So that's good for node 7. This is node 8. So we see that this node 8 is now becoming a 1. That's good. And I don't see any other node 8s, so we are good there as well. So now we look at these two. Oh, okay, there's a 0 here. Ooh, okay. So that means I missed something, okay? Because if you see on an ANSI row, there is a something, but on the corresponding PD row right above, that we don't see anything about that particular node, that means I missed something, okay? So you have to go back to the other node 3. So the other node 3 is right next to it. Okay, I somehow missed that one. So the other node 3 is over here. This is the other node 3, and it is the output of a NOT gate. Hmm. So did I miss something about node 2? Node 2 is the output pin. There's node 1. Oh, I know what I'm missing. It was my negligence. There's another node 1 here. So when this node 1 is getting a 0 in the NC, it should also propagate to this node 1 over here. I forgot about that. Okay, so I caught my mistake, right? So the important part is how did I catch it? So can somebody remind me how did I catch that I missed something? Exactly. Exactly. I saw that node 3 was updated here, and I go like, but there's no node 3 in the previous PD. So why is there no previous, change to the PD? So I tracked all the way back to, oh, okay, I forgot there's another node 1 over here. Okay, well, that's good. Node 1 is supposed to be a 0, so we're gonna change that to a 0. And unfortunately, I think that is okay. All right, so with this one, the in the PD, because this is a NOT gate, if the input of a NOT gate is a 0, the output is supposed to be a 1. So I can now say, okay, so this out or after a propagational delay, this is supposed to be a 1 now. Okay, and I don't have the. Well, I think this is good enough. Okay. All right. So because node 2 becomes a 1, okay, after a propagational delay, so that means the NC needs to reflect that too. So everything that is labeled 2 should be changed to a 1. So that would mean this one here, that should be changed to a 1. So we go to the text tool, and then I can now approximate the location of where it would actually put the text. All right. So because there's a 1 here, and this is a NOT gate, so in the next propagational delay, it should get a 0 as the output of the NOT gate. So that's also, so basically I just backtraced the entire, um, oops, that's supposed to be a 0. All right. Okay. So I'm going to double check again. This is a 0. From this 0 here, it changes to a 1 after a propagational delay. I need to update all the 2's to a 1, and this is the only 2 column that I can see. And then after that, it changes to the P. After one propagational delay, that becomes a 0. So I'm going to highlight the columns that I need to work on, okay, just so that I don't forget. So I know that this column I need to work on. There's one more. I know this column I need to work on. So I think those are the columns so far. Yep. Uh-huh. So you mean on the third row? You mean here? So these two zeros are coming from the previous propagational delay. Um, so the 0 of NAND gate A in 0 has to do with node 5, which is the output of AND gate P. And then the in one of NAND gate A comes from node 6. So that came from the output of the NOT gate H of the previous propagational delay. How do we get the 1? Because it's node 2. You mean this one? You mean here? Oh, under 8, this one? Hmm? To the left. You mean this one? Because once we know both inputs of a NAND gates are 0, the output is guaranteed a 1. Hmm? Yeah, but they're the same component. These are all component A. Okay. All right. The solution to this, the circuit. I did not draw the circuit in this one, so you can draw the circuit yourself. But if you want me to draw the circuit right now, I can do that too, just so that you can see it. Well, this one is a little bit. It has more, gates, but it's not really that different. So yeah, we can draw it. I'm just looking at, whether there are people missing in the class. There's one person who's missing. I'm just, because to draw this, I can draw that in Logisim. Okay. Yep. Unless I change, how the nodes are represented. Then it's like, what? Yes, you have to identify which part identifies the node, which is about connectivity, and which part specifies the components, which specifies the behavior, how the input relates to the output. So those are the two main things that you need to focus on. Anyway, I am going to draw the picture. So if you guys are interested in, drawing the picture before you answer the question, you're free to do so. I just don't do that myself. Okay, so whatever you want to do to help you, it's fine. All right. So what I typically would do is to identify all the input pins. I like to put all the input pins on my left-hand side and put all the output pins on my right-hand side. That's just the way that I prefer to put my pins. So whether you want to follow that or not is entirely up to you. So we have two input pins here, okay, D and E. So what I'll do is I'm just gonna draw those two over here. One is D and the other one is E. Okay, so obviously in the test you do not have access to LogicSim, but if you want to kind of get a better idea of how to do this, that's how you do it. So we have D and then we have E as input ports or input pins. Oh, this is supposed to be E. There we go. All right, so then we have output pins. Okay, so the output pin is out. Okay, where's out? There's only one out, which is Q. Okay, that's conventional. So the output is usually called Q. So we just keep it Q here. All right. So now what I would normally do is to start with the input pin and see what connects to the input pin. I'm going to start with D. It is connected to node 1. So that means it connects to a particular AND gate called P. So I'm going to draw a AND gate called P. Um, so we have to identify how many inputs there are. There are only two. So typically there are only two. It's not usual that we see more than two inputs to the gate. And this one is called P. So now I'm starting to identify the components. Um, so D connects to, um, it is node 1. So this is also node 1. It is the second input of the AND gate. So D connects to the second input of AND gate P. My mouse is not very sensitive, so I have to kind of do this carefully. So I may not have enough time to cover, how to draw the entire picture because, it does take a little bit of time. So now that I'm on P, so let's finish up, node, which node am I working on? Node 1. So I think that's the, no, there's another node 1 here, which is also going to a NOT gate. Okay, so now we go to the NOT gate, and then we say, okay, the same thing goes here. So I think that's enough to show you how to draw the picture. Whether it's worth your time to draw the picture, kind of is up to you. It does take up some extra time. I can just look at the components on the top and figure out what I need to do. So drawing the picture is taking extra time that I don't really need to use. But if you're more kind of visual, then it might help you better because you can track things a little bit better once you have the picture. So that's kind of up to you. So is that answering your question? How to associate the numbers to the nodes and how to associate the letters to the components? Yeah. Yep. Yep. So I'm not going to finish this, using this approach, because it's going to take a long time. So I'm just going to take that out. All right. So now what do we do? Okay. So it looks like the output pin is also missing entirely. So that's one thing that I need to track. Node 10 looks kind of empty to me. It might be something that I need to track too. So I'm just keeping track of, I'm just guessing, right now what I need to track. All right, so I think we are done with this PD and we are now moving on to the next NC. And this was the reason, that triggered me to kind of backtrack. because I knew that I was missing something. So that 0 is coming from this 0 here. Um, nope, I take it back. This 0 is, okay, that 0 is coming from node 3, which is coming from this 3 here. Okay, that is correct. Different component, they're both NOT gates. And then this 1 is coming from 7, which is this one over here. So that is accounted for. This one is coming from node 8, and node 8 is over here. So that's accounted for as well. Okay, so we are all good in this particular NC row. So after the NC row, then we look for updates. So in this case, knowing one of the two inputs of a NAND gate being a 1 does not tell me anything about the output, so it has to be left blank in this case. This particular one is one of the two inputs of also a NAND gate, so I cannot make conclusion about this output over here. And then this 0 is the input of a NOT gate, so that guarantees the output to be a 1. So I need to put a 1 over here. So that means at this point, I can now say, okay, this column is also something that I need to work on. So I really am just kind of marking the column so I don't forget to track that column in the future. All right, so there's only a single one here, which explains why there's a single one here, because they're both node 4. So this node 4 connects to this node 4 here. Everything is consistent. And then this node 4 is an AND. It's one of the two inputs of an AND. We know the other one is a 0 already. So 1 and 0 is still a 0, but it had a 0 as an output already. And that's why we do not do anything over here, because the state is not changed. Yes. Yeah, yeah. You can mark it up. You can kind of cross out things. As long as you put the correct answer into the right cell and I can see it, it'll be fine. Yeah, so I don't want anyone to tell me that, but I wrote down the answer in invisible ink. Just because you did not see it does not mean that I do not know how to answer the question. Not that it's anyone in this class has that tendency, but I'm telling you, in some of my other classes. Yep. Hmm. That is very creative. It is a mishmash of concepts. Okay, so what he's talking about is sine of x divided by n, right? Okay, that's no ink here. Okay, sine of x divided by n cancel out, so you have 6 left. Yep. Do you know what that reminds me of? Elon Musk. This is why I don't have a Tesla. All right. So another clue. Okay, this one is important too. This row of PD is actually empty. This is correct. Okay, but I can double check because on the next NC row you see a boldface one. The boldface one is always after a steady state. So that means okay, so we are good here. Okay, everything is accounted for. All right, so the next NC row has a boldface one here because we are changing this particular input port from a 0 to a 1. So the NC is going to propagate this one to whatever is connected to node 1, which is one over here, and there's also one over here. So this is how I can kind of remind myself, because of all the little marks on the up there, this one also has to be changed to a 1. So there we go. And now on the next PD row, I have to look at all the components that experience at least one of the input pins changing. So this is the first one, okay? This is now a 1, 1 for this AND gate, so the output should be a 1 instead of a 0. So this one, we need to update, and this is kind of a good indicator that this is one of the columns that I need to update. So now I go to the output of the AND gate and say, after the PD, we know the output of this one should be a 1. And then we look at the other one, which is this one over here. This is a 1, and so the output of the NOT gate needs to change to a 0. Yes. So, and one more thing I need to do is to kind of remember that's also a column that I need to remember to update. So I just put a little mark here, just as a reminder for myself. All right, so we are now done with this row. Nope, next one here. Next thing, okay, that should be it. So the next one is an NC. So we can see there's a 0 here, but there are no zeros on the next row. So I immediately know that something needs to be done. So we have to go take a look at all the node 2s and make sure all the node 2s get changed to a 0. So we have one node 2 here that was a 1, and it needs now to be changed to a 0. So the 0 goes here, and I forgot to highlight that column too. So this column also needs to be, I need to remind myself which column might get changed. All right. So we are done here, right? Okay, very good. And now this one is a node 5. This one is a node 5. This one is a node 5. I don't think I missed any node 5s. So the other thing you can potentially do is to draw lines, in the on the node, so it's easier for you to track, which ones are connected. Um, I would try, okay, but it's harder to do it with a mouse, okay. And I don't even use a mouse. I have a little touch point thingy on my keyboard. So one thing you can potentially do is to go like, okay, this is node 9, and this is also a node 9 over here, and then this is a node 8, and the next node 8 is over here. This is a node 10. You guys get the idea, right? So you draw a node 8, 10. There we go. So you can kind of draw something like that, but whether it helps or not, I don't know. Okay. Okay, so I'm gonna undo that, okay, because it actually distracts me. All right, so we are done with this particular NC row. And the next is a PD. Okay, so we have to look at all the updates. So for this particular NAND gate, we change one of the 0 to a 1, but the other one is still a 0. So that means the output is still a 1. So we don't have to do anything with the PD row. Huh? What if you put a 1 here? So the problem with putting a 1 here is it can distract you because you will then want to update the next N0 as a result, because we put a 1 only when there's an update. So it can kind of mess. It can potentially cause problems, especially when a PD row is supposed to be empty, so that we know it's a steady state, and you put something over there, then it's not quote unquote a steady state anymore. Okay, so about this one, okay, so this is a 1, and the other one is also a 1. So that means the output is a 0. It is correctly reflected here. It is one of the columns that are prefigured out already. And then the next one is over here. We now have a 0 for the input of a NOT, so the output should change to a 1. So we just use the text tool and then update this to a 1, like so. Okay, so do you guys want me to finish this or not? Okay. Now, do you want me to finish it because you want to understand the process, or you just want the answer, the solution? Say again? The process? Okay. All right. Because if you just want the solution, I can give you the actual key to all of these questions, and that will be a lot faster. All right. Hmm? Say again? Okay. I'll give you that. Sure. Okay, so now this is where things get a little bit kind of dicey. Huh? Well, that's actually impossible because I don't even know what I'll be asking. Yes, it is one of those things, and this is why I do not, come up with the questions too early, is just so that if people capture me and torture me and go like, give me the key to the next exam, and go like, I still don't have it. I really don't. Yeah, yeah. But I don't have that either. Yep, not yet. All right. So we just updated this row, and then the next row is an NC. So we just have to make sure. This is where it gets a little bit harder because I can't. The screen is only so big, and I don't have a spreadsheet version of this. With a spreadsheet version, it would be easier, but I don't. So so I think I cannot. Well, I can switch to the key, okay, and then just kind of scroll the key, okay. So let's do that. All right, so let's see what I'm going to do. Take this out. There we go. All right, so the key is this is a 310 from the previous semester, exam 2, version 000, and we're looking for the key. There we go. It's very systematic, okay? I know where to find my stuff. Hmm? So, yeah, so this is all highlighted, and I think we were done with the we were done with the first one, and we are now working on the second one. So we are done with this one here. So on the next row, we have a 0 here, and that 0 is coming from this 0 because it's a NC. And then because we changed the not, okay, I think we just worked this out. Okay, we worked all the way down here. And so from this PD, this one goes to the other one. It's still not easy to see because it's even though it's a table now, it is I still cannot scroll easily to keep visibility of the top. Now there's a trick to keep the visibility of the top. Yes, I know how to abuse tools to get them to work the way that I kind of need them to work. Okay, you guys are gonna you like this. So I think we are down to what, this one, I think. So this one of the PD, which is node 3, is now using the node connectivity to update the other thing that is also connected to the node 3. And then this is from node 7. It is updating the other node 7 over here. Okay. So is that what is that okay? Okay. So now we move down. Oh, this is a perfect ruler. Okay. It's a perfect ruler because it also, kind of gives me all the column number or the column information. So now, when we look at the NAND gate K, um, we have to look up, what is the other input, which is input one. Unfortunately, in this case, the ruler itself is covering the value of the other one. Oh, it's not. Okay, it's not covering, but we can still make a conclusion. Okay, let me explain. The reason why we can make a conclusion is K is a NAND gate. If you have at least one input of a NAND gate being a 0, the output is guaranteed a 1. So that's why we can update this to be a 1. And that would be a new column that we have to update. It's not previously updated. And then over here, with the NOT gate G, same thing. Okay, we change the input pin, and so the output pin also has to be changed. But because the output pins got changed in the PD, that means the NC has something to do following. So we have to make sure that they all got copied correctly. The one that is the output of K is node 9. So we have to locate all the node 9s to make sure they're all updated to a 1, and that's the only one. And then the other one would be node 4. Node 4 got updated to a 0, so we have to look up all the node 4. This is the other one, and that's the only one. So that's why we are only missing one cell on the next row. Is that okay? So this is basically the same way that we did the same PDNC analysis in class, except this one is a little bit longer and more complicated. It has got more components. All right. So I think we were done with the NC of this one. Okay, so now we look at the NC to try to figure out the PD. So that's the other thing that you have to remember is to determine a PD row, you have to look up the previous NC row. To determine the next NC row, you look up the previous PD row. One is just copying based on the node connectivity, that's NC. The other one look at the actual components and see how the input pin changes would affect the output pins. So that's how we differentiate between the two. So right now we're trying to determine the PD row, and we look up the NC row right on top of it and go, okay, what got changed last time? The NOT gate, I think we just did this one or not. I cannot remember. Okay, well, we can redo it. Um, So we see the NC of the above is changing the NOT gate over here. So this one is causing the 0 of the same NOT gate to change to a, this one of the input of the NOT gate affects the output, which is now a 0. The other input pin change is on NAND gate K, and with NAND gate K, the input was a 1, it is now a 0. And I think the other input pin was never known, but with at least one input pin being a 0 for a NAND gate, the output is guaranteed to be a 1. Is that okay? But that accounts for everything because I just look at all the input pin changes, and now we have done all the analysis. So now we move one row down again. Okay, so this time we're trying to determine the NC based on the PD. Same kind of thing. Um, I'm going to start with the right-hand side. Node 4 got changed to a 0 from the previous PD row. So that means on the NC row, we just have to make sure everything that connects to node 4 are also updated to a 0. So we just look up the numbers. Here's the other 4. It is already in the question itself. You don't have to do a single thing. And there are no additional node 4s. So we're done with node 4. And then we move on to node 9, which is the output of the NAND gate K. So that we now have to look up all the node 9s and make sure they all get updated to a 1 on the NC row. So 9, here's another 9 over here, and we don't see any more 9s on the left-hand side anymore. Huh? Oh, this one here, yes, but it's also already done, is a given. Yep, but you're correct. All right. So now we just, I mean, this is, at this point, it is really kind of iterative. So now we're trying to determine the PD row based on the NC row. So now we just look at the NC changes here. This is an output port, okay, an output pin. So with an output pin, it is not exactly a component. It can change the state. It doesn't affect anything else. So it's a dead end from the perspective of a PD row. However, this one, which is node 4, that is the input pin of an AND gate. So now we have to say, okay, what was the output of the AND gate? And if I move the ruler up a little bit, it was a 1. So if I move the ruler up a little bit, it was a 1. So now it has to be a 0. And that's why we see a new 0 over here. And then we look at, the first we look at AND gate B, NAND gate, sorry, NAND gate B. NAND gate B, at this point has 1, 1 in it. And because of, the other pin also known as a 1, for the very first time, we can now determine the output of NAND gate B to be a 0, because this is the only time, this is the first time we actually know the states of both of the input pins of NAND gate B. Is that okay? All right. So now We move down a little bit. Okay. So we are done with the PD. Now we are back to the NC. The NC rows are the easier ones because it's just copying and be careful. So we start with node 10, and then this is the other node 10. This is all good, and there are only two node 10s, and then this is a node 5. This is node 5, and I don't see any additional node 5s. So I think we're good. The node 5 is coming from here, by the way. This is the originating change, and then these two are updated because of node connectivity. We good so far? All right. So for the rest of it, it's pretty much the same thing. You just have to kind of keep rolling down a little bit more, and then there are no updates, after this, by the way. All right. So we are good with this kind of question. Okay. So the best way to do this is not to try to remember how we did it in class, okay, but to write it down, okay? Write down the way that I did it here in your own words so that you can follow, okay? Usually the process of writing it down is already enough because by the time you try to think about how do I write down the instructions to do this, it's already, in your mind, okay? It sinks in at that point. But having the written instruction with you is really just kind of like a boost of confidence. It's like, okay, in case I forget, I can follow my own instructions to get this done. Yep. NC, node connectivity, propagation delay. And it stands for propagational delay because after a propagational delay, from the time the input pins are changed to the time the output is affected, that is called the propagational delay. Question? Yep. All right, so this is question number 2. You are given the opcode of 5D in hexadecimal, and I use 0x to emphasize that we are dealing with a hexadecimal number. So part 1 for 20%, taking into consideration of opcode hijacking, figure out the mnemonic of the given opcode. So what do you do at this point? You're given the hexadecimal opcode. Yep, yep. It's so D would be 1101. Yeah, 1101 because it's 13. Mhm. But you're correct. So the general approach is to look at 5D as a hexadecimal number, and then you write out the actual binary number. So I'll just write it down here. So this is just all over the place. So it would be 0101, and then the second half is going to be 1101. So what do you do with the binary number? That is correct. So you have to match it up to the opcode table. So it is up to you to bring your own opcode table, okay? So you go to the opcode table, okay, which I have not shown for a while because we haven't had the need to do it. So print your own opcode table and bring it with you. Hmm? You can just write it down, whatever you want to do. You can, I mean, if you want to, you can annotate the opcode table with your own words, okay, which is the other way to do it. Hmm? It is copy register. Well, it is copy register, but remember the question said take into consideration of hijacking. So you have to be a little bit more careful because everything that starts with 0101 is potentially matching the answer. So now we have to say, okay, are there any 0101s? The answer is there are no other 0101, so copy register it is. So now you identify it is copy register. So now the question is, which two registers am I copying? Which one is copied to which other one? So now you go like, okay, XX is the one, which is register D, and then YY is 01, which is register B. Very good. Okay, so we are getting that part done. So, hmm, well, it doesn't matter in this case. I'm just asking what is the mnemonic, and that would be the mnemonic, right? Yeah. No, the TTP ASM does not make it illegal. It is in the context of a function or using the stack that makes it very dubious. No, it is not illegal because you can do some calculations with register B in order to move the stack pointer, and then after the calculation, you move the result back into the stack pointer. So it can be a part of sequence. You just gave me some idea for the final exam, by the way. Mm. Write down some little note here. Use CPR something D. But I think you helped to illustrate a very important point. Okay, so it is up to the context to decide whether something is a good idea or a bad idea. Okay, does it work within the context? So normally, okay, if you just go like, oh, we are just overriding the stack pointer, that by itself does not make it a bad operation, okay? Because if the result in B is already either incrementing because your intention is to deallocate something, or it is lower because you want to allocate something, then CPRDB is perfectly okay. So I may not be using the shortest sequence of instructions to get something done. I may be taking a scenic route, doesn't make it wrong. Yep. But it's important to point that out that in the final exam, I can give you a scenic route approach, and even though it's not the shortest sequence or the sequence that I use in the class, you still need to be able to identify the effect of the sequence. It's like, oh, okay, tech is just using extra instructions to get the same thing done. So, no, typically you can just use an add instruction to do that, but there's nothing wrong with calculating the result, putting it into register B, and then copy register B to register D. So that works too. Yep. All right. So what is the RTL corresponding to the mnemonic in the previous part? That's it. Okay, I'm going to describe to the video because in case that one person who's not in class is inclined to watch the video, I'm going to say tech is face palming 3 times. RTL stands for Register Transfer Language. Yep, it is column C in the opco table. Okay, so in the exam, I will not answer that question. Okay, so you guys have to be familiar with the term that we have introduced in the class. Yep. Hmm? Column C. Yep. So column C of the opco table, this is the RTL, and it says so. All right. So the more difficult part starts here. Okay, part three. Specify all the necessary endpoints, which are the ports, connections of components to implement the answer to the previous part. For example, for the instruction fetch cycle, it can be described as the instruction register .d, which is the D port of the instruction register, connects to the D port of RAM, and then the A port of RAM connects to the Q port of the program counter. Okay, so if you're If you understand what the instruction means, congratulations, you are understanding basically the basic layout of the processor. If you do not, I can try to explain here. Okay, all right. So the first thing you probably need to do is to get the picture of the processor, okay, get a map. And I think I typically would include a picture like this, okay, but it may not be at the size that you want, okay? So if you think that you have a better way to represent the mapping of the processor, for instance, you have already color coded some components, so that things are easier for you to read, bring your own, okay? I will give you something that looks like this, which is really just kind of basic and black and white. But even if it's black and white, I can still explain what I mean by that. So what I really mean is if you look at the fetch cycle, in order for the fetch cycle to happen, we need the output of the program counter to go through the multiplexer and then to go to the A port of RAM. So this is what we need for the first part of a fetch cycle because the program counter needs to connect to the A port so that it points to the location that we want to do the fetch. The other part that we also need for the fetch cycle, as an example, okay, is for the D port of RAM to go to the D port of the instruction register. So it has to go, eventually it has to go here. So I think we are pretty close. Just gonna follow this. Ooh, I cannot draw straight. There we go. So these two lines, okay, one blue and one red, they are representing, why RAM.A equals to PC.Q, okay, because the output of the program counter is called Q. It also explains why, we also say that RAM.A, oh, I just explained that one, but we also say, why instruction register .D, which is the input port, is connected to the D port of RAM. Okay, so this is, what we need to understand for each instruction. So now the question is, when we are dealing with the actual question that was asked. Okay, let me kind of scroll back to the question. So if I go back to the question here, we need to kind of specify all the endpoints. So in this case, the endpoints would simply be register D's A port, D port is getting register B's Q port because we always do the assignment, so that the right-hand side specifies the value, the left-hand side specifies what is changed. So in this case, the right-hand side, which is the Q port of register B, is going to the input D port of register D. Okay, so that would be the way that I specify the pathway that needs to be implemented. Okay. The instruction also says use register A to refer to register A. So that means, just to make it easier to read, you just add reg to the register identifier. So it's clear, it's not the D port, it is register D. Okay. Are we good so far with part 3? That is the answer for this part. Yep. So part 4 is to use the whatever we have in part 3, and then we just have to specify the values for all of these tunnels. There are some of these are not useful. Okay, for instance, okay, we know that the ALU is not really used in this case, so that means ALUEN should be a 0 to turn off the ALU. In which case, what you specify as the operation is not important. But the question also says, you have to use question marks and use the correct number of question marks to indicate the width. So you have to put in like 3 question marks for ALUOP because that's a 3-bit wide port or tunnel. Is that okay? All right. So let hmm? I believe it is also in the document over here. Doo-doo-doo. Yep. So it only the question asks you to kind of explain why that is the case too. So these are the explanation. So whether something is disabled or not used, and if it is used, which pathway is it used? So it's like it's identifying, in order to make all of these happen, you need these particular tunnels to be configured in this way. Since we are not using the ALU, we want to disable the ALU, and that's why ALU EN needs to be a 0, and then ALU OP is a question mark because it's not used, and so on. Question? Nope. Okay. Looks like you might have a question. Mm-hmm. Yeah, I misspoke. Just a single question mark. The question did not ask for the right number of bits because many of these they are all base 10 numbers. So the three, you know, should have been a 1 1 if I want the correct bit width. Yep. So that was not the case. Yes. Correct. Now, the important part of getting these questions done is to really know the map well. Okay, so that means you have to go to the map over here and kind of really know what tunnel serves what purpose. Okay, so it is about the purpose of each tunnel. What does it do? Which multiplexer does it control? Which demultiplexer does it control? Which demultiplexer is it enabling or disabling? And so on. So understanding that is really important. And the way to practice and also to prepare for the exam is really just to kind of practice with another person, okay? Or you can do it yourself too. Pick a particular mnemonic, okay? Let's say or AB, okay? So we pick or AB or AB, and then what we do is we just have to kind of try to answer this question in this particular format, okay? So you the first part we cannot do, okay, because the first part is I give you the hexadecimal opcode and you have to go back to the mnemonic. So, but in this case, you start with the mnemonic, you can go back to the opcode. But then you can answer the rest of the question or at least practice answering the rest of the question. Are we good so far with this? You can verify to a certain point, okay? So you can verify to the point where you can confirm the ones that are in fact in use or have the value that you specify. But what Logisim cannot tell you are the ones that are not used. So the not used are the ones that you kind of have to figure out if okay, let's say a multiplexer is disabled. So whatever goes to the select of that multiplexer is not used. So so the not used is a little bit harder to figure out. Not from Logisim, you kind of have to figure out if this component is not used, then things that are connected to it would not. I don't need to specify those. For instance, if yep, yeah. So if RAM cell is a 0, so that means RAM load is going to be a question mark because if RAM is not active, then it doesn't really matter whether we are loading or not. Yep. So are we doing okay so far with how to approach this kind of question? Okay. And how to practice? Because I want to give you guys, make sure that you know how to quote unquote study. Because studying for this part is not your usual studying where you have like pages of things to memorize and read. This has to do with the map itself and understanding how the components interconnect with each other to get a job done. So are we good so far? All right. And getting familiarized with the components is then really helpful. So if you're going like, I kind of remember how a multiplexer works, but not really, you can just print out, the page, for the multiplexer and bring it with you just in case you need that piece of information in the exam. I will show you a trick. And some of you would go like, "Ooh, okay, that's interesting." And some of you go like, "I don't think I need that," which is okay. We all study differently. All right. So I will show you. Where did I put it? Okay, I'll put it in the temp folder, so just so that I have a copy, I don't mess up the actual thing. So I'm going to copy um, Logisim over here, and I think it's nope, it's inside the subfolder. So I'm copying Logisim 310.jar in my temp folder, just so that I don't mess up the original one. And then I'll do this. I'm renaming logisim.jar to logisim.zip. Okay. I don't need to do it on the Linux system, but you need to do it in Windows. Okay. So rename so that the extension goes from jar to zip. Once it's renamed, you can unzip it. A jar file is really a zip file with certain types of files. So now you go like unzip, logisim 310.zip, gives you a bunch of stuff, right? So within that bunch of stuff, okay, so we go to, it's not source that we want to get into. Let me see, resources, net, nope, I cannot remember. All right, fine, we'll find that. Doc, okay, go to doc as a subfolder. So now when you go to doc, you can see that it has EN, okay, so if you want to do Spanish, you can go to ES. If you want to do Russian, you can go to RU. If you want to do Deutsch, you can go to DE. So it's up to you. If you can go fancy, you can go like, oh, I can use this to practice my foreign language class. More power to you. Not a problem, man. I'm just gonna go to EN. So why this is interesting is because all the help files are actually here. So you go to HTML and then you go to libs and then you go to, let's say we want to look at the web page to describe a multiplexer. Okay, so that would be plexers, and then go to plexers, and you have, it has its own index page. Okay, you can always just go to the index page and go from there. So you can now go like, okay, I'm gonna use my typical browser, okay, Google Chrome, and open index.html, and it looks like a normal web page like this. You go to multiplexer, and it looks like, oh, okay, this is exactly the same help that I saw when I used, the internal help feature. That's exactly it. Okay, this is it's just an HTML document. Okay, but because it is outside of the help dialog box now, it is in a browser. What can you do with a browser? Woo, print. You can also copy and paste it into a Google Doc. Only keep the parts that you think are really helpful so that you don't have like a huge long document to read, during the exam. Okay? Hmm? You can annotate, you can take out stuff that you think, okay, I got this part already. I just really need to know these two parts and how they work. So you can do whatever you want, okay? Because you have the source document now. Okay, so this is a nifty trick to get to the document itself so that you can actually do your own editing any way you want. Okay, so are there any questions about number two? Question number two. The answer is here already, so you can actually just read the answer and make sure that you understand the answers. The exam is next Wednesday, which means next Monday is also a day where you can ask questions. So you can watch this video again, go through the key, and go like, I don't understand why that tunnel has to do with establishing a path between these two ports. Go ahead and ask the question then. Okay, so I always schedule the exam so that we have one more lecture in between for people to ask questions. So use that opportunity to ask questions. All right, so now we are moving on to the question number three. All right, so question number three is about floating point numbers, I think. Yeah, that's question number two. Oh, okay. I guess not. This is a this is a different semester when the double question was in the first exam. That's okay. I can find the first exam too. So we'll go ahead and find the first exam and talk about that. Okay. So the first exam, the last question is a double. Let me see. Yep. There you go. Okay, it is quote unquote question number 4 of the first exam, but it will be your one of your questions in exam 2. All right, so the question is asking if you are given z equals to a binary number times 2 to the power of 5, you're also given vdx equals to blah blah blah, where x represents a 64-bit pattern to be interpreted as a IEEE double precision floating point number. um, then the rest of the question is using that as a context. Okay, so question number 1, or part 1 of this question, is step by step show the value of z represented by a base 10 decimal number. Okay, so how do we do that? Well, you just have to translate this binary number to the decimal version and then multiply that by 32 and you get your answer. So you can bring a calculator with you because some of these, powers of two is a little bit harder to track, so I understand if you need a calculator to do some of this. So the way we do this, okay, I will show you my math, and the best way to do it is to do it on the whiteboard, unfortunately. Yeah, sure. So in this case, we have what 1.10100001 in base 2. Okay. So there are two ways to do this. You can just go with the powers of 2. So we have 1 of 2 to the power 0, 1 of 2 to the power of negative 1, 0 of 2 to the power of negative 2, and so on. But then you'll be working with really negative powers of 2, which I don't really like working with. So the other approach is to look at the 2 to the power of 5, because you can now go like, oh, okay, I just have to move the decimal point 5 times to the right hand side. So that means 1, 2, 3, 4, 5. There we go. So you take out this one, you move it over here by 5 positions. So that makes it a lot easier to work with, in base 10, because now we have a quarter. Okay, this is a quarter. We have this is 1, 2. This is 4, 8, 16. This is 32. So you add up these, you have what 52 and 25, I think. Okay, now i can I can cheat a little bit because I have the key to this one too. Yep, that's the answer. All right, there we go. So now we proceed to part 2. So part 2 asks you to compute the biased exponent of 2 and represent it as a base 10 number. So we already have the mantissa up here. The mantissa, this is already a mantissa because it is between 1 and 2, excluding 2 itself. So that makes it this a mantissa in base 2. So this is the exponent that we want, but it's not biased. So now you have to remember, what exactly is the bias in an IEEE double precision floating point number? 1023. And what if somebody tells me, but I cannot remember that kind of thing? Yes, it is right there. This is why I provide the actual way to interpret a 64-bit number. So 1023 is the bias amount. So if 5 is what I need and the bias is 1023, that means the biased exponent is 1028 because you just add those two together. So 1028 would be the answer to part 2. And now I need to convert, G, which is the answer to part 2, to a binary number. So 1028 1028 is 1020 plus a 4. That makes it really easy because now we have both of those as powers of 2. Um, 4 is 100, and then 1024 is 2 to the power of 10. So that means I need to make up 10 digits before I put the 1. So we have 1, 2, 3, and then 4, 5, 6, 7, 8, 9, 10. Put a 1 here. And that becomes the binary representation of 1028. Okay, you can still use the same technique that we use for base conversion when we talk about base conversion. That works too. I personally can remember most of the powers of two, and that makes it easy for me to do it this way. Are we good? Okay. All right. So that's part three, and then part four says assemble all the bits of a double X, being the 64-bit pattern. Explain where the bits come from, and you can use the 0 notation, but then indicate the number of zeros. So in this case, the sign is going to be a 0 because the amount or the value that we want to represent, which is z, is non-negative. And then we have the 11, no, we have the 12 digits of, wait, yeah, we have 11 digits for the exponent, and the exponents would be what we see here as g on the whiteboard, and then followed by the mantissa, but only the fractional part of the mantissa. So that means the mantissa part would exclude the one from the 1 point and only include 1010001, and then the rest are all zeros. And then you just have to make sure that you have enough zeros on the right hand side to make up for 64 bits. So that would be the binary representation of X as a bit pattern, a 64-bit bit pattern. And then number 5 is just to convert the binary number into a base 16 number, which means you chop the digits by 4 chunks of 4, and then convert each chunk of 4 into its own hexadecimal number, and then you are done. Hmm? Huh? Say again? For number 5, number 5 applies to whatever you end up with number 4. So all the parts chain, you know. So if somebody gives me an incorrect answer, um, I may or may not give partial credit for the following part because I can see, okay, let's just say that somebody does not know anything about base conversion. Okay, so and they gave the answer of number 4 to be all zeros because that would make it very easy to convert the whole thing into hexadecimal. In that case, I would give 0 partial credit to number 5, and most likely 0 partial credit for number 4 as well. On the other hand, if somebody gave me, for the most part, correct for number 4, maybe off by 1 or 2 digits, and then number 5 is completely consistent with number 4, I will give partial credit. Is that okay? So partial credit is not always guaranteed. It depends on whether I can see a intention to to exploit partial credit by making an earlier part of the answer a easy one for the later part of the answer. Huh? If I were a math professor and I see this kind of answer, I'll make sure that that person get a negative score for that question because it is just it is that bad. Yes. Just to see what happens. I see. All right, so let's move on to the lab for today. We do have a lab today, and this is the first time you actually get to write some code. Yay. Hmm? Okay. So these are the two activities. So there's one that you have to do during the lab time, and there's one that you have to turn in. So the part that you have to turn in, you don't have to turn in until the 17th. It's not even next Wednesday, because next Wednesday we are having our exam. So I want to give you like the extra weekend. So this is the Monday after next week. Okay. So that's when the homework is due. But the function call, the actual lab activity is actually due today because that's the part where you have mostly multiple choice questions, missing parts, and stuff like that. Um, all right, so I will let you guys get started with the lab once I tell you the access code. So the access code is, oh, I don't have one. Okay, well, cool. No access code then. No, the homework, the submission part has no access code. Yep, yep. Alrighty, so let me stop the recorder. Whenever I do something like this, a part of me is always kind of like, did I start the recording? Yeah, I did.